Well, hello, dear friends. Welcome to the introduction to the Logistic Regression lesson. So in this lesson, we're going to discuss classification problems, how to use logistic regression to solve them, and how to interpret the results of logistic regression to read the confusion matrix. All right, so let's get started. Now, classification is a problem of determining which categories a new observation belongs to on training data. Some examples of classification problems include trying to detect spam for spam, trying to determine if someone is paying off their debts, or even trying to diagnose a disease. For example, trying to find out if someone has cancer. Now, all of the above examples are binary classification, meaning that we have two classes, right? So far, we have seen regression problems in our studies where we only try to predict a continuous value, such as the price of a house. Although the name may be confusing at first, logistic regression allows us to solve classification problems where we try to predict discrete categories. The binary classification rule is to have two classes, 0 and 1. However, we cannot use a normal linear regression model in a binary group. It doesn't fit well. For example, if we look at the graph below, we have a y-axis that represents the probability of belonging to a particular group. Let's go ahead and imagine this example conspiracy trying to predict the probability of repaying a loan. So we'll go ahead and label their loans with a 0% probability of default, meaning they'll 0% likely to repay their loans. And at the top, our probability of repaying loans in full is 1, or 100%. We'll go ahead and mark the x-axis as some sort of paycheck value. So if we go ahead and look at this data, as your paycheck drops, your probability of repaying your loan approaches 0%. However, as your paycheck value increases, your probability of repaying your loan has not approached 100%. Now, the reason these yellow lines are all 0% or 100% is because it's training data. Now, what if this was trade data and we try to use a linear regression model on it? Well, we would have a very bad fit. In fact, we'd have to guess the probabilities below 0%, which really doesn't make any sense. So instead, we can convert our linear regression to a logistic regression curve. And you're going to notice that our logistic regression curve can only be between 0 and 1. And this will be key to understanding classification using the logistic regression curve. By the way, it's also known as the logistic function. So the sigmoid will be key to understanding how to use logistic regression to perform a classification. Now, the key secret to this function is that it can take in any value, and its output is going to be between 0 and 1. So the function of z is equal to 1 over 1 plus e to the power of negative z. Now, the main thing to note here is that it doesn't matter what value of z you put in the logistic function or the sigmoid function. You will always get a value between 0 and 1. So again, if you take a look at this graph, it doesn't matter what value you put in for z. The output on the vertical axis will always be 0, well, between 0 and 1. So this is the key to the sigmoid function. So this means we can take this linear regression solution and insert it into the sigmoid function. And that will look like this. Note here that our linear model follows the basic principle of y equals mx plus b. Here we have a linear model as y equals beta none plus beta 1 times x. So we take this linear model and put it in the sigmoid function. We can finally transform this linear regression into a logistic model. So whatever the value of the linear model output actually is, it doesn't matter. When we put it in the logistic model or the sigmoid function, it will always be between 0 and 1. So it results in a probability from 0 to 1 of belonging in the 1 class. And again, no matter what we put in this horizontal reach, it will always get some kind of probability between 0 and 1 on the vertical axis. So this means that we can usually set a breakpoint at 0.5, and if anything below results below 0.5 or 0.5, that will go to 0 class. And then anything above belongs to class 1. So we're going to transform that 0.5 probability as a cutoff point. So we'll go ahead and do a quick recap overview. See if you can tell me what we've just discussed. Okay, I'll tell you what we just discussed. We can use a logistic function to output values ranging from 0 to 1. And again, it doesn't matter what we put along the vertical axis. We get a value from 0 to 1. So based on this possibility, we will be able to assign a class. Now this makes sense by putting a cutoff point, 0.5, because we want to be able to tell if the probability of belonging to the first class is 50% or less. And then we should classify it as class 0 in our binary classification. Now, if our probability of belonging to class 1 is 0.5 or higher, we'll go ahead and assign this new point to class 1. All right, so let's talk about model evaluation and using a confusion matrix. So after training a logistic regression model to classify some training data, you're going to want to evaluate the performance of your model on some test data. So you can use a confusion matrix to evaluate classification models. Now, the confusion matrix, this is a table that's often used to describe the performance of a classification model over a set of test data for which the actual values are already known. The confusion matrix itself is actually relatively straightforward to understand. However, sometimes the related terminology can be a bit, well, confusing. So let's go ahead and examine this example, shall we? So in this case, we have a binary classification problem. So in this example, we'll test for the presence of a disease where no is a negative test, which is false equals 0. Yes is a positive test, where true is equal to 1. Now, what can we learn from this matrix? Well, just straight off the bat, there are 2 possible predicted classes, right? Yes and no. If we were predicting the presence of a disease, for example, yes would mean that they have the disease. No, it would mean that the patient wouldn't have the disease. So the classifier made a total of 215 estimates. That is, 215 patients were tested for the presence of the disease. Out of those 215 cases, the classifier predicted a yes 135 times and no 80 times. So in fact, we already have labeled test data. In this sample, 130 patients have the disease, 85 patients do not. You see that? So we'll go ahead and define the most basic terms. Basic terms are the integers that it specifies. So the odds don't just keep the numbers. And these terms are true positives, true negatives, false positives, and false negatives. Now, if you've done a lot of studies on vaccine controls or disease control, you may already be familiar with this terminology, but if not, we'll review it. True positive, yes. Cases that we presume to be illness, and they actually have the disease. So that's TP, true positive. So in this case, you can find it here at the bottom quadrant where TP is equal to 120. True negatives are these places where we know that illness doesn't exist. And again, actually, they don't really have any illness. That's why it's up here on the upper left-hand corner, TN, and that's equal to 70. So that's true positives and true negatives. They do not contain false positives and false negatives. False positives are where we predict yes to have a disease that they didn't actually have. It's also known as a type 1 error. False negatives are where we estimate that they have a disease that they don't actually have. And that's known as a type 2 error. Then we can talk about rates. So the first rate we can discuss is accuracy. And what this really shows us is how often is it true in general. A lot of times when you hear reports on studies, they'll just tell you the accuracy. And the accuracy is calculated by the number of true positives plus the number of true negatives over the total. So in this case, our model is 88% accurate. Then we have the misclassification rate. And this actually answers the question, how often is the model wrong in general? So this will be calculated by the number of false positives plus a number of false negatives divided by the total. So that's 25 divided by 215. Typically, this is the 11% error rate or misclassification rate. So now let's talk about false positives versus false negatives for a nice quick way to remember it, or your type 1 error versus your type 2 error. So remember, the false positives that I pointed with a mouse here, FP equals 15. Yeah, so that's where we guess, but they don't actually have the disease, right? So that's type 1 error. False negatives are what we guessed is no, but they actually have a disease, so this is known as type 2 error. And so, my friends, we can go ahead and think of it as a nice way to remember type 1 error and type 2 error as this funny little diagram. So a type 1 error is where you're telling a man they're pregnant. Again, you're predicting, yes, they're pregnant, but they actually don't have any, well, they're not pregnant. The type 2 error is a false negative. So here you're saying to someone that's obviously pregnant that, no, you're not pregnant. So you're predicting no, but they actually are pregnant. And that is a good visual for the difference between a type 1 error and a type 2 error. False positives versus false negatives. And statistics are commonly referred to as type 1 or type 2 instead of their actual names, false positive or false negative. So I hope that's a nice, very useful, and a little bit of a fun reminder of how to memorize these terms. So we'll begin to explore an example of logistical regression using the famous Titanic data set. Oh, that sounds intriguing, huh? We are going to use Python to predict whether a passenger will survive based on features. Okay, dear friends, thanks a lot, and I look forward to seeing you in the next lesson. All right, see you then. Hello, dear friends, and welcome to another lesson of logistic regression using Python. So, I'm really excited about this lesson because we're going to be working with a huge data set. This is a very famous data set, actually, and it's often a student's first step in machine learning for classification. So we're going to try to predict the classification, survival or death for passengers on the Titanic. And we're going to use a semi-clean version of this huge data set in the data set. The original source is actually from kaggle.com. So why don't we just get started? Okay, my dear friends, if you jump into the machine learning partitions folder under Logistic Regression, you're going to see some files here. These are the test.titanic.csv and train.titanic.csv files. And these are the data sets that we're going to work with. So just go ahead and use these two CSV files that have already been downloaded for you. And the notebook we're going to be using is Logistic Regression of Python. All righty then. Now let's go ahead and jump straight into a new notebook. So first up, and as always, we'll get started with imports. I'll do Pandas as PD, NumPy as NP, and then I'll just go ahead and do my visualization imports. So I'm going to say matplotlib.pyplot as PLT. Likewise, I'm going to import Seaborn as SNS. And then since I'm using this notebook, I'd like to say matplotlib inline. All right, so we're going to go ahead and start making a Pandas data frame by reading the train Titanic CSV file. So I'm going to create a data frame called train, and I'll say pd.read_CSV. Actually, I can start typing train, and if I click on the tab here, it'll autocomplete with these options available for me. Okay, so in this case, I want to train_titanic.csv, and we'll run this, and then I'm going to go ahead and check the head of the data frame just to get an idea of what's inside. Yeah, so it looks like we have a passenger ID column, a survived column, and you're going to notice this is 0 or 1. That is 0 if the passenger did not survive, and 1 if the passenger survived. So the passenger class, the P class column, can be first class, second class, or third class. That is, depending, of course, where on the ship the passengers had purchased their passage. There's also the passenger name column, the sex column of the passenger, that is, whether they're male or female. The column here, the age column, of course, is the age of the passenger if it was recorded. And then this SIB SP column, showing the number of siblings or spouses on board. And then the column par SH shows the number of parents or children on board. And then there's a ticket number column, passenger fare column, approximately how much they paid for the ticket. Yeah, so there's a cabin column, which is the cabin that they're in, if it's known. And then the column embarked. And that's part of the yield, namely C for Cherbourg, Q for Queenstown, and S for Southampton. Okay, so these are the basic columns. And let's go ahead and get started with some exploratory data analysis. Now, most of the time, you got to know, right, we'll have missing data. We will continue to create a simple heat map to see what we've missed most out of our data using Seaborn. So I'm going to go ahead and do this. So I have training data, and if I say is null, or is null. Let's see about using this as a method. So I'm going to go ahead and just let me show you what this looks like first, at least what the output looks like. You'll get an idea of what we're doing. So these data frames are huge, right? I've already said that, but basically you get true and false Booleans. So false, obviously, if not empty, or true if empty. So remember back to that very first cabin, it was NaN. So it was unknown. It was null. So it went ahead and put true there. So with this kind of data frame, I can actually make a heat map. So I'm going to call it sns.heatmap. And then I'll add a few more arguments so we don't get a lot of tick labels. And I'm going to say y tick labels equals false. And I'll go ahead and say C-bar equals false, because we don't want to make any real color stick. And then finally, I will pass CMap as VIRIDIS. So we'll go and see what this gives us. Okay, so be careful with what I've created here. I've created a heat map, right, from these Boolean values. So these are true and false statements. And thanks to this CMap, every yellow line here is color matching, representing a real point where it is basically empty. So we can now order and check the data from a remote bird's eye view. Yeah, so some of the age column information is missing. A lot of the cabin column information is missing. And only one line of the embarked column sequence is missing. So I'd say about 20% of this age data is missing. So I can really use the information of the other columns to fill in the reasonable values for that age column. So I'm looking at the cabin column. See that this data is missing too much to do anything really useful with it at a basic level. So you know what? We're probably just going to go ahead and drop that later. But let's go ahead and visualize this data a little bit more. So we'll come back to the problem of dealing with missing data later, because that's a whole issue in and of itself. So we're just going to go ahead and make a few more plans to do some exploratory data analysis, just, the visual cursory level. So I'm going to go ahead and say SNS set_style to white grid. Now, I personally think it looks a little better, as I prefer this style, but to each his own. Now, the first thing that I want to do is just take the number of those who did not survive and the survivors for the classification problem, right? So it's always a good idea to just see the proportion of actual target labels. So now we can do this for a simple count plot. So I can say SNS.countPlot. And then I'm going to go ahead and set the X to survived column. Set my data to train, and then go ahead and run it. All right, so as we can see here, I have quite a few more people that did not survive versus the one column which represents survived. Now, gosh, they should make a movie about this, huh? But anyway, it looks like around 550 of these passengers in this data set did not survive. And it looks like about, well, in this particular training set, we have about 350, maybe a little less, that actually survived. So it seems that there are fewer survivors than those who did not survive or died. So we're going to go ahead and do another count plot so that we can see survival with the hue of sex, as it's called. And actually, I can add this hue. So I'm going to say hue is equal to sex, and this is going to add some color. So I can be able to surmise the survival rates by gender. Okay, so I'm going to go ahead and add a palette argument to make this a little easier to see. So I'm going to do rdbu underscore lowercase r. Okay, so now the males are blue, the females are red or light pink, just depending on your monitor. Okay, so for me, this makes it a little easier to read. All right, so looking over this plot, I can say that there really is a trend here, right? So those who didn't survive were apparently far more likely to be males, and survivors were almost twice as likely to be females. And when we look at the factors and coefficients that would cause someone to survive, we will see this trend emerge a little later. So let's go ahead and continue exploring the data by changing this hue to the passenger class. So I'm going to go ahead and call it P class instead of sex here. And for the passenger class, I'll go ahead and remove this palette and just use the default palette. Okay. So again, looking at this, we can kind of tell the trend here with survived versus not survived. And it looks like the people who did not survive were overwhelmingly part of third class or the lowest class. In other words, the cheapest class to buy a ticket into. Don't want to make any political assertions. This is just data. The numbers tell a story. So it seems that the ones who survived were leaning toward the slightly higher classes, 1 and 2. Now, we will also have to see how many people are actually in the passenger class or per passenger class. But we'll be doing that analysis. So let's go ahead and get an idea of the age of the people on the Titanic. So to do that, I can go ahead and do a distribution type plot. So I'll just go ahead and say sns.distplot and pass in the age column. Now remember, distplot only takes an array of values. So for now, I'm going to go ahead and say drop NA because I don't want these to break my distribution plot. Also, KDE equals to false because I just want to see the histogram of these values. And let me set the bins to something a little higher, like 30. All right, so let's run that. Okay, so we have something interesting here that almost appears in the model distribution with quite a few passengers between 0 and 10 years old. So there are quite a few children in this area. But after that, you can see that somewhere out there is starting to get an average age towards 20 or 30. So it's quite possible maybe it's skewed towards younger passengers, and the older you get, the less representation you have on board. Okay, so let's go ahead and show you another way that you can dist plot. If you weren't a big fan of Seaborn, you can always do that. I'm not going to judge. You cannot be a fan of Seaborn. But you can always do something like dot plot hist directly in the age column. And Pandas' own visualization can do this for you. So here we'll say bins to something a little higher, like 30. Again, and we'll get a similar looking graph. Okay, so let me go ahead and go back to the Seaborn real quick. And let's go and explore some of the other columns just to get a reminder of what those columns are. I want to go ahead and call info. So this is the call info method. Okay, so we've already checked out the survived column quite a bit. We've seen the P class, the sex column, the age column. Let's go ahead and explore that SIB SP, and that was the number of siblings or spouses on board. So let me go ahead and do an sns.countPlot. Set x equal to sib_sp. And my data that I'm going to use is the train data frame. Okay, so now looking at this plot, I can basically immediately tell that most people on board did not have either children or a spouse on board. So that's interesting. If we look at the second most popular option, which is actually most likely to be probably a spouse versus just having a single parent with a child on board. So according to those numbers, pretty much it makes sense that you have a lot of single people on board, yeah? Probably those are men in the third class, maybe. And after that, you have the second most common type of passenger in our data set. Now, this is some of the just one either sibling or spouse, and that's probably going to be their spouse of couples on board. Okay, so we haven't explored the other columns yet. One is the fare column. So let's go ahead and take a look at how much people paid as a distribution. And we're going to go ahead and do this with Pandas. So I'll say train fare. So now if we take a look, keep in mind that these, well, they're basically just the prices that they paid for. Now to call a histogram, I'll say .hist. Let's go ahead and run this and we'll see what we got. Okay, so we immediately see that there is a fairly wide range of values. Most distributions seem to be somewhere between 0 and 100. So to get some more detail, I am going to increase my bins size to 40, and then we can also kind of stretch it out, passing in fig size to maybe 10,4. Okay, so it can now get a higher distribution or higher level of detail in this distribution, to be more precise. Cool, so it seems that most of the purchase prices are between 0 and 50. And again, it makes sense to distribute these because they're cheaper tickets, because as you can already see, most passengers are actually in this cheaper third class. And this isn't me, this is just the way it was in 1912, so these prices haven't been adjusted for inflation. So let me just go ahead and I'll show you an example of how we can make this type of plot with cufflinks, if you really like interactive plots as much as I do. All right, go ahead, twist my arm. So we could say import cufflinks as CF. And then we tell cufflinks we want to work offline. Then we go ahead and essentially do the same thing. So grab the fare column of a train, and then we just say iPlot to see this in our plot, and say kind of equal to hist. You can specify more bins, and then let's see this run. So I can go zoom in and check these bins myself and add more bins. So I want to put 50 bins. Zoom in and see where I am most interested in and use this. Okay, so my friends, there are many things that you can do with Python. Very powerful language, and there are many great libraries for it. Okay, so I'm going to go ahead and comment this out right now. And you know what? We're going to end this lesson here because we finished our exploratory data analysis. Okay. So to recap, we went ahead and kind of explored the data without really knowing too much, except with our historical ends, of course. And we saw the distribution of fare prices. We saw the accounts of siblings versus spouses on board. made an assumption that most of them were probably single based off of this count, or just had one spouse. We went ahead and checked the age distribution, and we also looked at survival and passenger class and survival and gender. So, again, we can see that mostly men are in the non-survival group and mostly female are in the survival group. And then we found that we had quite a bit of incomplete information, and we wanted to find out how we can deal with the age column and this cabin column, right? So we'll continue in the second part of this series of lessons and discuss how to deal with missing data. All right, my friends, so thank you to everyone involved. I'll see you in the next lesson. Well, hello, my dear friends, and welcome to the second part of Logistic Regression in Python. So in the first part, we focused on exploring data through visualizations. And in that exploration, we actually found that we have, I would say, to categorize it, quite a lot of missing data. But that shouldn't stop you. What we want to do now is shift gears to cleaning our data. So cleaning our data will enable us to transform our data into an acceptable form for our machine learning algorithms. So we'll go ahead and go back to the Jupyter Notebook where we were last time. Okay, so here I am in Jupyter Notebook. And if you remember from the last time, we used a little trick with the train is null method. We did SNS heat map to quickly create a map visualization of where the missing data is located. But instead of removing all the missing age data rows, we want to fill in the missing data for the age column. Now, of course, one way to do this is to enter the average age of all passengers. This is known, yes, this is a technique. It is known as imputation. And that means you can just take the average age and fill in the missing values with that average age. However, we could actually be one step smarter in this regard and check the average age by passenger class. Let me show you how that works. All right, so I'm going to scroll down, and I'm just going to go ahead and create a box plot using Seaborn. With X equal to P class column and Y equals to the age column. And it will be equal to train in my data. All right, so let's go ahead and run this and take a look at our box plot. So what I'm going to do is set this to plt.figure. Fig size is equal to. And let's go ahead and make this, let's say, 10 by 7. So it's a little bit bigger. Okay. So we can now zoom in on the center points of the box plot. So here, split by class, we can see that wealthier passengers in first class and second class actually tend to be slightly older than third class passengers. Now, you might think, okay, well, maybe that makes sense because, well, it could take age or time to accumulate wealth, reach material wealth of the first class or whatever. So if you have enough time to accumulate enough wealth, you would probably be older, more likely to be in first class, yeah? Well, then what we can do is use these average age values to determine the age depending on the passenger class. See where we're going? So now if you wanted to, you could create an entire model to try to predict age based on all the features. So you could go ahead and use the sort of simple imputation, which is a little better than just imputing the average age. So why don't we just go ahead and create a function to implement this function, and you'll see what's going on. I'll just say impute underscore age. And this will take an argument called COLS inside. And then I'm going to go ahead. Yeah, so what I'm going to do here is essentially say age is equal to cols 0. So the first item here, and then we'll say p class is equal to cols 1. So the second item at index 1. And what I'm going to say here is if pd dot is null of age, and then I'm going to have some if statements here. If p class is equal to 1. So one of them in the first class. And I'm going to go ahead and return the average age for passengers in the first class that occurs at 37. So if you want to get the exact value, what you could do is just go ahead and actually get the average by class using Pandas. Or if you wanted to, you could create a box plot using Plotly and just do it that way. So here I'm going to say return to 37. And then if the p class is equal to 2, meaning in the second class, I'm going to go ahead and say return 29. And then finally, else, meaning they're not in first or in second class, but they still have null for age. And I'm going to go ahead and say return 24, which is the average value here for the third class. And then I'll say else. If my value is not empty, I will return their age because I already know. Okay, so that's the function, and we're going to go ahead and apply that function. So I'm going to say train, age is equal to train. And now I'm going to pass in age and the p class column. So a list of these columns and dot apply. And I pass in the name of the function I want to apply. And then say x is equal to 1. So I want to apply this across the columns. Yeah, so it ran correctly. Now let me go ahead and quickly explain what's really going on here. Are you ready for that? I'm sure you are. So I've created a function here that takes an argument, calls, and notice here that it actually grabs, based off my index values, the age and p class. And I'm able to do that because I'm using that apply these two columns. And then I'm going to say if pd dot is null, that age. So at that particular point, then we check by passenger class. If it's first class, we return the average age for the first class passenger. If it's second class passenger, return 29. Otherwise, if it's third class, return 24. And of course, if they're not a null, then we actually know the age and we just return that age. And then I went ahead and I applied that function to these two columns here. And then I said axis equal to 1 to apply it to the columns. And now we can go ahead and check the heat map again. So I'm going to say Seaborn or SNS dot heat map. Train dot is null. And set y tick labels equal to false. Now I'll just go ahead and set C bar equal to false. So if we run that, we get this color mapping scheme. And what I do is I set my color map to Veritas because, well, it's just easier for me to see. Okay, so you see how it looks like we no longer have any missing information for the age column. So that means we've successfully placed values that are reasonable estimates for people's age, and we get that data from other classes. Now, the issue we have now is the cabin column. And to be honest, there are just way too many missing points to do something, that's useful for that column. What you can do is maybe try to create a new feature that tells us that we know 0 or 1 for the cabin. But again, there's a lot of missing information here. It's easier to go ahead and just drop that cabin column. So in order to do this, I'm going to say train.drop cabin and state that the axis equal to 1. And then I'm going to go ahead and say in place is equal to true. And if I check out train head, do you notice that when you go ahead and scroll, you're going to see that there is no cabin column anymore. And if I go ahead and run it, now pay attention to this again. Now we only have that missing value embarked. And since this is essentially one row of some missing information or, 1 or 2 rows. So I'm going to go ahead and drop more missing values. So I'll say train.drop NA and set in place is equal to true. So now I should have no missing values. So I'll go ahead and run this one more time. Okay, so you see how everything now has a single color. Nothing's missing, and that means we're good to go. All right, so we've taken care of the last step of cleaning our data, and that deals with the missing values. So we went ahead and we filled in some missing values, and we went ahead and dropped some other missing values. Yeah, so now what we have to deal with is the categorical features. We'll use Pandas to convert the categorical features into what's known as the dummy variable. See, otherwise our machine learning algorithm cannot take these features directly as input. So that's all to say, let's do something like this. If you see that the sex column here, we categorically have a male or female feature, right? Well, a machine learning algorithm isn't going to be able to take in just a string of male or a string of female, so we'll have to create a new column. In short, to encode this information in a way that a machine learning algorithm can understand it, it's necessary to implement a method that's known as the dummy variable. Something similar can happen inside the embarked column. So we'll have a look at the embarked column here. It's just a letter representing a city. And again, a machine learning algorithm won't be able to just take that letter and immediately know what to do with it. So they'll need something in a dummy variable format, which is going to indicate a 0 or a 1 with a column as an actual value for a particular city. All right? So let me just continue to explain this in a little bit more detail by showing you some of the examples of how we can do this with Panda. So I'm going to go ahead and say PD and use the get_dummies method. And of course, you can go ahead and click on the Shift tab. And you want to explore this method a little more. Actually, this method is basically just going to convert categorical variables into values known as dummies, or otherwise known as indicator variables. I just like saying dummy, I guess. You big dummy. Anyway, we're going to pass in the column that we want to convert. For example, the sex column, male, female. If we do that, pay attention to what we pull out. Now, this has a little problem. One column here is a perfect predictor of the other column. So if our machine learning algorithm feeds both columns, for example, if the machine learning algorithm sees 0 in the female column, it will perfectly predict that it will be male. You follow? So this is a problem known as multiple linearity. It's basically going to mess up the algorithm because a bunch of calls will be perfect predictors of another column. So yeah, that's something to know because we've got to avoid it. And in order to avoid this, what we got to do is, as another argument here, we are going to go ahead and say drop first equals true. All right. Then we'll go ahead and drop the first column. And now this is exactly what we want to feed into the machine learning model algorithm as a column. Now we're going to go ahead and equate this to the sex column. Sex column is the data frame of whether this person is male or not. And now we're going to do a similar thing for the embarked column. And we create a data frame called embark. And we said embark equal to pd.getDummies_train embarked. We'll go ahead and say drop first is equal to true. Now run this. And then I'm going to go ahead and check out the embark data frame. Just ahead of it. And look here, it went ahead and dropped the C column, and now I have indicators of Q and S. But notice one call or all columns are not perfect predictors of each other because it went ahead and dropped that C column. Now what we can do is say train equals pd.concat, and we'll just use concatenation to add these new columns to our data frame. So pass in a list of the data frame to concat, and we train and then the new sex and embark data frames. And we'll say axis is equal to 1 because we want to add them in the new columns. And we'll check out the head of train. And we'll get something that looks like this. Yeah, so let's just have a look at the top two rows here. Yeah, and then we'll go right and notice that these new columns, male, Q, and S, so these will be the pillars to replace our machine learning algorithm. These are the indicator or dummy variables. So what this means is we don't really need these other columns anymore. So we no longer need this embarked column because we already encoded it in Q and S. Likewise, we don't need the sex column anymore because we've coded it into this male column. What about the other columns? These are things like ticket column, name column. There's really not much information we can use there. Of course, you could try feature engineering and new features like grabbing the first letter of the ticket or the title of someone's name if you want to. That's always a fun exercise. We're not going to do that here, but you can go ahead and do that on your own. What we're going to do is go ahead and just drop the column. So that means we're not going to use it. So we're going to say train.drop, and I'm going to pass in the columns. And I'm going to use sex column because we already coded that into the male column. Likewise, for the embarked column, not going to use that column because it's already encoded in Q and S. And I'm not going to use someone's name because really there's no way to easily pass that into a machine learning algorithm. 10 points extra if you do, but I'm not. So maybe we can feature engineer some stuff off of that. No. It actually gets quite complicated since we're dealing with text data. Not really the focus of the course here. So what we'll do is fill in the ticket column and drop, because there's really no easy way to grab information from a machine learning algorithm with that either. All right, so finally I'll say axis equals 1 because I want these to drop from all rows of the columns and set in place is equal to true for this situation to be permanently valid. Okay? So now let's look at the header of our data frame. Cool. This looks perfect for a machine learning algorithm. All data is numerical. Everything is together. So now our machine learning algorithm works perfectly. So the last thing that we want to look at, this first numeric column, passenger ID. Notice that this passenger ID is actually just an index starting from 1. So let's go ahead and check the tail of the data frame. Yeah, exactly the same thing, just an index starting at 1. So that just means that even numerical ones are essentially not useful for predicting whether passengers will survive based solely on their position indexes, right? So yeah, we'll just go ahead and say drop pass in passenger ID. And say axis equal to 1. And we'll say in place equal to true. So let's just go ahead and check the head of the data frame one more time. Okay, so now let's take a quick last look at the columns. You know, it never hurts to double, triple, or whatever check just to make sure everything is fine. And we have the survived column, which is 0 or 1. And that's good because that's our label column. We have the P class column as the numerical indication of what class they were in. We have the age column of how old the passenger was. We have the SIB SP column, how many siblings or spouses they had on board. We have the PAR CH column, how many parents or children they had on board. The fare they paid, whether or not they were male, whether or not they embarked at Q or not, whether they embarked at S. The interesting thing to note here about the P-class column is that it is actually a categorical column, meaning it can only have 1, 2, or 3 different categories. That means that we could have also done pd.getDummies on that column. But you know what? I'm just going to leave that to you. Why don't you pick that up as an extra exercise to do after you've already run the model with it as a normal column just by itself. And this is because I want you to explore the differences between leaving it alone as 1, 2, 3 columns and using the pd.getDummies of the separation of these categories. And then you'll be able to discover on your own how a machine learning algorithm will react to a column treated categorically against one that is a continuous variable. Okay, dear friends, that's it for part 2. So what we did in part 2 is go ahead and clear the data, reading incomplete data filled with some other data. We also learned how to use the getDummies function to create and deal with categorical columns. So coming up next, the final steps, where we're actually going to create and train and build our machine learning classification model using logistic regression. All right, my friends, thank you to everyone involved, and I want to see you in the next lesson. Well, hello, dear friends, and welcome to Logistic Regression with Python. This is part 3. In part 1 of this lesson series, we did some exploratory data analysis with some visualizations. In the second part, we cleared the data by handling categorical variables and missing data. So now in part 3, we're going to train and use the model to predict whether a passenger will survive on the Titanic. So let's go ahead and go back to the notebook that we started last time. Okay, so here I'm in Notebook. Here we have the data set. So one thing to note here is that if you go back to your folder, you'll notice that there is a test_titanic.csv file and a train_titanic.csv file. So I'm going to go ahead and cover this training set here, or train it as if it was all of our data. So I'm going to go ahead and review train test split process. What you can actually do is do the same cleaning on the test.csv found here and use it as your test set. Now, since they actually have two separate CSV files, in order to go through the process of using scikit-learn train test split, I'm going to go ahead and treat this train data frame as if it was all our data. Okay, so let's go ahead and see how to do this. First thing that we have to do is split our data into X and Y. Notice that Y is the column from which you are trying to predict the actual label. So in this case, that's going to be the survive column. So I want to predict a 0 or 1 in that survive column. Everything else, just going to be the features. So I'm going to go ahead and say X is equal to train.drop survived, and axis is equal to 1. Now I can go ahead and say from sklearn.model_selection import train test split. And then there I can use the tab for autocomplete. And what I like to do is say train test split, and if you shift tab in the Jupyter Notebook, you can see the documentation stream. Now scroll down a little bit until you get to the example. And you can just grab this, copy and paste. So I'll copy that. And I'll paste it into replace that and put it now all on one line. Okay, so here you have my X train, X test, Y train, Y test. And I'm doing train test split. I'm going to go ahead and set my test size to 30% and set my random state to 101. Now, of course, like I said earlier, you don't need a random state, but if you want your results to match mine, boom, just put it in as 101. All right, so let's go ahead and run this. Excellent. Now we have data for X test, Y train, Y test, and X train. So now the next step is to actually train and predict by creating a model. Now for logistic regression, we'll go ahead and grab this from the linear model family. So I'll say from sklearn.linear_model import logistic regression. And we can go ahead and run that. So for the next thing, what I want to do here is create an example of the logistic regression model. So I'll just go on and create logistic regression. We'll go ahead and call our model log model. And the next step is actually training the model. So if you do Shift Tab here, it will give you some more information about the various parameters you can add, but we'll just go ahead and say .fit xtrain and the y_train and run it. All right, so now we're going to make some predictions using this, our X test data set. So that means we'll go ahead and say predictions equals log model.predict, and then just pass the X test because we want to predict values off of that X_test. Perfect. So that's it. If you don't count the train test split, we can actually create a model, fit a model, and predict a model in just 3 lines of code. Now, this is actually very reflective of real-world analysis and machine learning building process. But a lot of times, most of your work as a data scientist is actually going to be cleaning data, getting that data into an acceptable form. In other words, here in a machine learning algorithm. So the machine learning algorithm libraries that you'll be using are actually sufficiently complex and abstract enough that the process of building them will actually be quite simple. So that's why I say most of your work will be reflected in the cleaning data set. Okay, so now let's go ahead and evaluate our model. For classification tasks, Scikit-learn has a really nice classification report you can use. You can say from sklearn.metrics import classification report. And the classification report will basically tell you your precision, your recall values, accuracy, the F1 score, and some others. And that way, you don't have to get busy reading a confusion matrix yourself. So I'm going to go ahead and say print classification report. And then you pass in your true values y-test, and then your predictions. So run that and report back the precision and recall for each class, as well as the average total and supporting cases for it, besides the F1 score. Now, if you don't want the classification report and you want the pure confusion matrix, sklearn metrics has that too. You can say from sklearn.metrics import confusion matrix. And you can say confusion matrix and pass in the same thing, y-test predictions, and you'll get the actual confusion matrix to evaluate your model that way. Now, in that way, in case you really want to compute a very specific value, you can do it straight from the confusion matrix. Okay, so considering we're dealing with a smaller data set by splitting our training data instead of using the train and test CSV, these results are actually not that bad. However, you may want to explore other ways to increase your precision or recall or accuracy. So what you can do, actually there's a couple of things you can do. Maybe just try using the entirety of the training set versus comparing it to the test CSV after you repeat the cleaning process for the test CSV file. Other things you can do are more feature engineering, such as trying to grab the title of the name. So in other words, to treat that as a feature, like Dr., Mr., Mrs., the title. And maybe the cabin letter could be a feature as well. Also, the ticket column might have some information for you to do. So go ahead and continue exploring this project as you see fit. There are lots of things you could do. In fact, there's some more information at kaggle.com and how to get started with doing this sort of analysis with Python. And you'll get very, very familiar with it. You'll get so adept, you'll be able to come up with your own methods. So go ahead and check it out. Kaggle's link is available in your notebooks. Now, you will see when you examine that they usually use a random forest machine learning algorithm. But since we haven't learned about tree methods quite yet, you might want to hold off there. But for now, I hope you've enjoyed this project, because coming up in the next lesson is going to be your actual project exercise. You're ready for it, don't worry. All right, my friends, thanks again, and I'll see you in the next lesson. Well, hello, dear friends, and welcome to the Logistic Regression Project Exercise Overview. So here we're going to go over the notebook for the Logistic Regression project. I'm going to go ahead and show you where you can find it. I'll just jump into the notebooks now. Okay, so here I am under the Logistic Regression folder, under the Machine Learning Sections folder, and there you will find a notebook labeled Logistic Regression Project, and another notebook labeled Logistic Regression Project Solution with, guess what, solutions for the project. So I'll also be using this advertisement.csv file, and this will be the data source for our project. So let me go ahead and quickly explain the Logistic Regression project. So in this project, we're going to be working on some data underscore of underscore add, and data underscore of underscore add indicates whether a particular internet user clicks on an ad. Some people might say whether they want to or not. So we're going to try to create a model that will predict whether they are going to click on an ad or not based on the characteristics of that user. The data set also contains various columns and attributes such as age of the customer, income of the customer, the topic line of the advertisement, is the consumer male or not, which country do they live in, etc. Okay? What you are going to do is go ahead and go through the data, import the libraries that you need, do some exploratory data analysis with some visualizations, and then toward the end, what you're going to do is actually do the logistic regression. So that means that you're going to do a train test split, train the model, and browse a classification report. Okay, dear friends, that's it. Enjoy the project, and I'll see you in the next lesson. Well, hello, dear friends, and welcome to the Logistics Regression Project Exercise Solutions. And hopefully you have gone through the project and are just here to congratulate yourself because you want to make sure that you've done everything the way that we've taught you. Well, we are going to go over the solutions of the Logistics Regression Project, but we'll have to see how you do. So we'll go ahead and jump into the notebook to get started. And as you can see, here I am in the notebook, and I'll go ahead and start the missions. So the first thing that you want to do is import several libraries. I'm going to go ahead and import the ones that we usually import, NumPy and Pandas. And I'll also import the visualization of libraries that we use, such as Matplotlib.pyplot as PLT. Import Seaborn as SNS. And then Matplotlib inline. This way I'll be able to see the visualizations in my Jupyter notebook. So we want to read the advertisement.csv file as data underscore of underscore add. You can do that with pd.read underscore CSV. Now we want to check the header of data of add. We can do that just with the head method, and we get these columns back. All right, so here we have the columns of consumer time on the site in minutes, customer age in years, average income of geographical area of consumer, average minutes a day the consumer's on the internet. The headline of the advertisement, that's the ad topic line. The city of the consumer, whether or not the consumer is male. The country of the consumer, timestamp column, which the consumer clicked on an ad. Okay, so next we want to use the info method and the describe method on the data of ad. So you can go ahead and just say data of ad.info and it returns back, 1,000 rows, 10 columns. And if you want a statistical description, you can just go ahead and say data of add.describe. And you can see some statistical information about numeric columns. So go ahead and continue with some exploratory data analysis with some plots. So we want to, and we create a histogram of the age column. And you can just call directly age column.plot.hist, or even just .hist, and set bins equal to 30. And let's check it. Okay, so here you see a histogram of the age column, apparently fairly normally distributed species around the age of 30, 35 years old. It's a little hard to say. All right, so the next plot, we want to do a joint plot showing area income versus age. So we'll go ahead and explore that. You can just call sns.jointplot. So on the x-axis, we want age. So I'll say x equal to age. And on y, we're going to say y equal to area space income. And then we'll say data source equal to data of add. And then we get this joint plot that appears like this. So we can kind of see the relationship between the area income versus the person's age. Yeah, it's a little scattered, but it looks like there may indeed be a trend that you start earning once you start getting into your 20s. That kind of makes sense. Then as you get a little older, it looks like your income perhaps starts to rise. I guess that's what everybody hopes. But as you get even older, even towards retirement, either you start getting no income or, well, that source kind of drops. Okay, so we can go ahead and take a look at a joint plot showing the KDE distributions of daily time spent on the site by age. That's going to look like this, and it's going to show you how it'll do that. So let's say sns.jointplot. So we want to pass in age as x, and on y, we want to go ahead and say daily time is spent on site, which is the name of the column. And then we're going to say data is equal to data of add. All right, so let's go ahead and take a look at this. Okay, so if you notice this, if the type's not specified, we get a scatter plot again. So I want to go ahead and say kind is equal to KDE. So here I'll take this nice KDE diagram, and if you want to, you can go ahead and set the colors. You can say color equals red, and that way you see the distribution red. All right, so now we can create a joint plot of daily time spent on site versus daily internet usage. So you can say sns.jointplot and say x is equal to daily time spent on site, and y is going to be equal to daily internet usage, where data is equal to data of add. So now let's go ahead and explore this a little. So what does it look like? Notice I'm just going to keep the colors their default blue. Now it looks like we can definitely see two clusters here, right? Your daily internet usage increases, and consequently daily time spent on the site increases. So you tend to belong to this cluster here. This paired diagram looks almost like a circular pattern, huh? And then what we can do is, in order to explore it a little further, let's just do this joint plot for every single numerical column. So let's go ahead and do that with an SNS.pairPlot, and we want to pass in data of add. So now we also want to say hue defined by, clicked on the add column. And I'll go ahead and run it. Now keep in mind that a pair plot may take a while, depending upon how large your data set is. All right, so there are default colors here, and if you want to increase the size, you can just zoom in on this, or just notebook or style, whatever you like. All right, so in fact, we can see quite clearly certain relationships between things like age, income, or daily time spent on the site, or whether they click on the ad. And of course, if that piques your interest, you can go ahead and discover that on your own. So what I'm going to do here is move on to logistic regression. Now, all I want to do is split the data into a train set and a test set using the train test split. And to do this, we'll say from sklearn.model_selection, import train test split. And then we can always say train test split. We can do Shift Tab. I always like to scroll down to see the samples. And you can just copy and paste from the sample. Makes your life a little easier. And then we can go ahead and say X and Y. Test size going to be 0.3. I'm going to set random state to 101. And you'll get the same results if you're following along now. So what we want to do is set X first, and that's going to be the data of add. And if we look at the data of add again, we go ahead and create a quick data of add.head. So let's look at the first line and see what we really want to pass. All right, so I want to pass in actually all numerical information because it looks good. All right, so then the columns that I want to drop are some string information like country or city, or even add subject line. I also need to get something from the timestamp column so that it is not missing. So we'll go ahead and just drop that as well. So let's go ahead and just grab the columns that we're interested in for data of add as features. That's going to be the daily time spent on site. Next column we want is age. Also, we'll take the area income and the daily internet usage column. And whether or not that person is male. And that should do it. All right, so those are the columns that we're going to be using. And then for a Y, this will be our target column. So Y is equal to the data of add. And from this data, we can get the click and add column. Okay, so now let's run the code cell. Yeah, sure enough, they look good. So this means we can train the logistic regression model and fit it to the training set. So I can go ahead and say from sklearn.linear model import logistic regression. Okay, so now we can say log model. Go ahead and instantiate logistic regression. I'm just using tab here, and I'll go ahead and fit that to X-train and Y-train to my training data. So I've created my model. Now I can predict values from it. And I can say the predictions are equal to the log model, the point predicts, and I can pass in my test data. All right, so I'm ready to create a classification report. So I'll go ahead and do that first. I'll say from sklearn.metrics, import classification report. And don't forget, we should measure also so that we can do the confusion matrix. And I will say print classification report and pass in Y test and predictions. And you can do the same thing if you want to print confusion matrix, just pass in Y test and predictions. So this gives you a bunch of information. In this case, it looks like we're actually doing pretty well. We're getting around 90% on the precision recall, 93% around for accuracy. Yeah, so it turns out we actually have a few mislabeled spots that aren't bad given the size of our data set. Now you can also clearly see that the blue and the green data for some certain features are here. It is actually quite separate. So this is a good indicator of some things. I know you know what. Don't worry about it, though. I hope you enjoyed the project. It should have been pretty straightforward, but, some of the instructions were deliberately left a little ambiguous. So, you'd actually have to refer to the lesson, especially some of the things like the splitting of the data were left as a single line to split the data, even though it involves multiple steps, right? Choosing the X and Y values, stuff like that. But I know you got it as soon as you get more comfortable with it, especially with Scikit Learn and Python's machine learning. It's just gonna be so natural. You could do it in your sleep. You will be doing it in your sleep because I dream about this stuff. Okay, so thank you again, and I hope to see you in the next lesson.